Oh, okay. So hello, everyone. Welcome back to DSP. Let's start today's lecture, right? Um, so first of all, still, I'd like to briefly tell you what's today's agenda, okay? So from last time, recall that we talked about, finally we mentioned what it means for signal to really become digital, right? The key step is quantization. We need to represent our numbers in zeros and ones. So here, the idea is still, we have a continuous time signal, and then we convert it to, we sample it, so that it becomes a sequence of number denoted by x of n being integers, right? But still here, these are real numbers. There could be any real number, and it has the unit of, let's say, volt. Okay, signals have unit. And it even has a unit, could be any arbitrary unit. Say, could be millivolt, could be centimeter, could be temperature, and so on. Etc. Right? So these numbers are physical quantities. 这是个物理量啊。So to really be able to process them, store them, and make transmissions, 要处理、要储存、要传输 right? So everything needs to be really converted to represented by zeros and ones. And that's how we mean digital signals. So in one way or another, we need to perform quantization. We need to perform quantization so that the result becomes x hat of n by approximating x of n to the sort of nearest integer, rounding it to the nearest integer. Okay, and this, and in general, we'll have an error, approximation error, hat being some kind of representation, and this will introduce some approximation error in here. So error can be denoted as, let's say, the result subtracted by the original. Okay. So today, our first topic is to go back to quantization. Okay. So we'll show that last time in the end we showed that quantization is really pretty simple. We have a kind of staircase function, 像楼梯一样啊。The I/O function, let's say before and after quantization. Before and after quantization, really the difference is that we have a staircase look like something like that. Right. Okay. So we'll start from here and study some property of the errors. Okay. Is the error, for example, is the error independent to our original signal? Is the error itself like white noise? Is it uniformly distributed? Such are a few issues that we can study together about the properties of the approximation error. Then after that, so that's the first topic. So then we will just after that, we will briefly talk about converting back to analog from digital. Okay, so we'll also touch base on that. So in practice, how do we make sure that the resulting analog signal has no spectral distortion, for example. Okay, so we'll just briefly talk about that. I'm not gonna elaborate on this too much. 我们今天不会讲太多这个，好吧？ We're just gonna briefly talk about D2A. A few concerns. So now after A to D, D2A, so in general we have a framework for digital signal processing. Okay, the entire chain processing, starting with a continuous time signal and ending with a continuous time signal. Let's say this is y of n, and this is y reconstruction of t. Okay, so that will pretty much conclude all I want to say about chapter 4. Okay, these materials can be found in the textbook in chapter 4. And today I also want to start a new lecture, lecture number 5. So this is lecture number 4 in my notes. And today we will also start lecture number 5 with some review of linear and time invariant systems. Okay, so in this next lecture, we will talk about linear and time invariant system. And we will also explain that such systems, turns out that at least for discrete time, we can describe the system completely by an impulse response. Okay, so what matters is all you need to know is the impulse response. We will typically denote as h of n, and we'll show that for such kind of linear and time invariant systems, the output equals to the input convolved with the impulse response. Okay, so we'll talk about convolution, and also this is a good time to introduce Z transform. So I hope that we have time to get to here. Okay, we'll officially introduce Z transform for any signal in discrete time. Okay, do they always exist? There is a question mark. Okay, so that's about what we can expect to learn today. So far so good. Okay, so let's come back to quantization. All right, so let's just take it easy and come back to quantization. So in here, so here is where we were at last time. Okay, so as you can see, we have this I/O function, which looks like a staircase, right? So output versus input. And again, you see that output is denoted by a hat, 加个盖子 hat, 帽子 hat, x hat. X hat is the result after quantization, where Q stands for to quantize a signal, okay? or simply a number, really to quantize a number, right? The I/O function is staircase because this shows us that this is just nothing but rounding to the nearest integer. It's nothing but just 四舍五入 in Chinese, rounding to the nearest integer. But what do we mean? So we need to introduce a few parameters, okay? So the idea is that we quantize with finitely many bits, right? So let's say in this case, we are going to use 3 bits to represent all the numbers, all the real numbers. Only 3 bits for this example, right? And we know that when we are given 3 bits, then there are only 8 possible values. We can represent only 8 possible values with 3 bits. That's pretty obvious. 2 to the 3 bits binary number, right? With zeros and ones, and there are only 8 different possibilities, right? So in this case, we have the 8, 1, 2, 3, 4, 5, 6, 7, 8. 8 steps. And the step size, so this height from one step to the next, this distance is denoted by, in this case, denoted by letter delta. And we call delta, it's very simple, we simply call delta the step size of quantization, okay? So once we determine the step size, then, and we know that we have only 3 bits, right? So the full range here, when we sum up all the step size, when we multiply the step size by 8, that's our full range. Is it clear? Yeah. We have 8 possible values, right? And actually, you might be able to, let me see. So we have 8 possible values. So if we sum up, we multiply the step size by 8, that gives us the full scale, okay? So here, the full scale is So I want to just show you a simple relation. Yeah. So a simple relation. We have, so I want to just write it down, okay? What's the relation between delta and full scale? We have full scales, but full scale here, the range here really, by definition, is 2 times full scale, okay? Or sometimes this is called full range. Full range includes positive and negative side, okay? Positive or negative. So full range is equal to 2 times full scale. So we must have delta should be full range 2xm divided by 2 to the number of bits. In this case, b equals to it's so stupid. 2, yeah, you know what I mean. 2 to the power of number of bits, okay? I hate this notation, number of bits. Usually I don't do it, but there's a reason. Yeah. So delta equals to full range divided by 8. 8 being 2 to the 3rd power. Yeah. Is that clear? Okay. So this is kind of important simple fact which defines our parameter and their relation. Delta is simply full range divided by number of steps, right? And number of steps is equal to 2 to the 3rd power. So far so good. It's pretty easy. Okay. So now let's focus on the right. Okay. So now we have mentioned that suppose that we have 3 bits to encode all the numbers. Right. But we haven't mentioned. What we haven't mentioned is which string, which combination with 0 and 1 represent what range, which step. Okay. We haven't talked about the mapping from the step values to the binary representation. And there are different choices. There are actually different choices. For example, we can choose to encode our steps in strictly monotonically increasing order. Okay. The lowest one is represented by 0, 0, 0. The highest one denoted by 1, 1, 1. That's one possibility, right? So this is just binary 0, 1, 2, 3, 4, 5, 6, 7. Okay, 0 to 7, 8 different possibilities. Right? So that's one way. But it turns out that the more common way of encoding the steps is called 2's complement. 2's complement. And this 2's complement is nice in that 0 corresponds to 0, 0, 0, which makes a lot of sense, right? 0, the value 0 here corresponds to, the analog value of 0 corresponds to digital sequence of 0, 0, 0. And that's one thing to notice, okay? And anything that is positive, the remaining 3 levels are represented by number 1, number 2, and number 3. Just naturally, okay? Yeah, does everybody see that? This is number 1, number 2, number 3. Yeah, just a good old binary number. But the negative side, we see that this is also in the increasing order. Yeah, in the increasing order with the lowest one now encoded as 1, 0, 0. One step above that is now 1, 0, 0 plus 1. That's 1, 0, 1, right? And then we plus 1. That's there. And we add 1. That's there. And finally, if we just still add 1, then everything's reset to 0, 0, 0. That's the meaning of 2's complement. Okay, that's a good example of 2's complement. Okay, yeah. So far so good? Yeah, 2's complement. So now I have an exercise, okay? Suppose that we now we recommend using 2's complement. There are reasons that this encoding scheme is recommended. There's a reason because it's probably easier if we talk about arithmetics, 算术. It's more convenient for arithmetics. Yes, but anyway, so this is the way, for better or for worse, this is the way we recommend any analog number to be encoded using the scheme of 2's complement. 2's complement. So I have an exercise next, right? So now suppose that we are encoding our number with how many bits? 8 bits here. Okay, 8 bits here. And suppose that we have a full range of 2 times xm. Then, in particular, what does this number represent? What step value does it represent? That clear? So this, by the way, we're kind of jumping ahead. You know, if you can solve this problem, then you are solving. You are doing a DAC in your head. Let me say that again. If you can solve this problem, you are doing digital to analog conversion in your head. Seriously, okay? So the question is, now we are given an arbitrary sequence of ones and zeros. In this case, it starts with a 1. The most significant bit is a 1, right? Indicating it's a negative number. Okay? Yeah. Remember that in 2's complement, the most significant bit here indicates the sign. Okay, in this case, it's going to be a negative number. But how about, when we put everything together, can we calculate the digital to analog conversion in our head? That's the question. That's the question. Okay. Think about it for 30 seconds. Okay, how do we calculate DAC? Digital analog conversion, given a sequence encoded in 2's complement. Think about it for 30 seconds. Okay, so let us try to solve it together. Okay, solution. So we have the most significant bit. Okay, the most significant bit is 1. Multiplied by 2 to the, should it be 7? But it's negative. That's the tricky part. The first one is the sign bit. Okay? But actually, the rest is all summation times 1 plus 1 times 2 to the 6th power plus 0 times 2 to the 5th power plus 0 times 2 to the 4th power, and plus 1, 0, 0, 1. You can actually find this formula. There's a formula in the textbook. You can actually find it. Plus 0 times 2 to the 2nd, 0 times 2 to the 1st power, which is 2, then plus 1 times 2 to the 0th power, okay? This is the corresponding integer. When we talk about rounding to the nearest integer, this sequence represents this integer. Okay, that's an integer represented by our sequence of 11001001. So shall we, explicitly calculate it? Minus 128 plus 64. Really, this is seriously what we mean. Plus 8 plus 1, okay? Equals to what? You can calculate. It's probably minus something. Minus something. Minus, can anybody tell me? Seems to be minus 55, okay? If my calculation is correct, okay? But then, what it actually represents, of course, this number represents this integer, but going back to analog, we need to multiply 55 by the step size. Okay, the step size now. So we answer is, x equals to minus 5 times our step size is 2xm, the full range divided by 2 to the number of bits, which is 8. So that's the answer. So we have something like 256 at the bottom. So minus 55 divided by 256 times xm. That's the answer. Okay. That's what this sequence represents back in the analog domain. It may have a unit depending on our full range. Okay. The full scale xm, is it in the unit of volt? Is it in the unit of centimeter? Is it in the unit of Celsius? Okay, yeah. Okay, so any comment? Does everything look correct here? Yeah. Yeah. Oh yeah, 谢谢. No wonder it looks really kind of strange. Yeah, 128. Yeah, thank you very much. 我故意的, no. I made a mistake. You see, trivial things, but we are all human beings. So I'm not AI, right? I made mistakes. Yeah. Good. Okay, so yeah, so that's pretty easy. So now we have we can go freely from analog to digital with binary representation. And we can go back from binary representations back to an analog value. So things are in good shape. So now we can, now I would like to spend some time to talk about the noise. After we round all the numbers to nearest integer multiple step size, what will the errors be like? What will they look like? So a bit about the notation still. We have the input, okay, first input, and then we have, we denote the result of quantization. The quantizer really is a function, is this function. This is a function. This is the qx, okay? This picture denotes our, this is a plot of our function q, quantizer, what the quantizer does. So as a function of the input, we have the output, okay? We have the output after rounding to the nearest integer, multiple of step size of delta. But it turns out that we prefer, in the following discussion, we prefer to think about quantization not as a function, but as if we are introducing error by addition, by summation. Okay, we are summing our signal with our error to get the final value. This is just a mathematical definition. Okay, this is just a fancier way of saying that E of n is defined. I use a triangle. Is defined. Even is simply defined as the result after quantization subtracted by the original value. That's the definition. But when we rewrite, when we rearrange the terms around, yeah. But when we move xn to the other side of the equation, then we have this representation, this way of thinking of quantization as if we are introducing an error. Or sometimes this error is called quantization noise. Okay? E of n, you can call it quantization noise. Quantization noise, okay, or quantization error, quantization noise. By quantization, just equivalently, we think of it as if we are introducing an error term, a noise term. Okay? But then we can ask a few questions. The error, is it really good to refer to the error, to call the error a noise term? Yeah. When I say noise, what comes to your mind? What do you define noise? What is noise? What is noise? 讲中文也没关系啊。What is noise? What is noise? 杂讯。What is 杂讯 ？Unwanted things are called noise. Okay. Anybody else? What is noise? The outside is noisy. What is noise? Right? What is noise? Unwanted, something that you don't want to pay attention to. Okay. All right. So now we really seriously have a question. So when we say this quantization error is something we call it noise, there got to be some reason why we can call it noise. Okay. Its statistics really look like noise, for example. 它的统计像是杂讯嘛啊。So in the next few slides, we're going to show some statistics of an example. Okay, and in this example, we have a analog, a discrete time sequence, which is defined, which is basically a periodic signal. Okay. Which is basically cosine with a period of with a certain period. Okay, so this is basically a periodic signal that's plot in here. This is cosine for sure, right? And this is before quantization. Okay, so quickly, in this example, in the bottom in plot B, we are showing the result after 3-bit quantization. Yeah, 3-bit quantization. And so again, we have only 8 possible values, being the lowest 1, 1, 2, 3, 4, 5, 6, 7, 8. 8 different levels. 8 different levels after quantization. So this is before, this is after. Okay, before and after quantization. So remember how we define quantization error? Quantization error is after subtracted by before. Right, the difference basically. So now, if you can imagine what would the different signal look like? The difference is a signal, okay? So let's again write down, this is, according to our notation, this is after quantization, and the result is x hat n, and this is before quantization, we denote it as xn. So the difference is our quantization error. The difference is defined as xn subtracted by xn. I mean, the first one has a hat. Okay, yeah. So can you imagine? Yeah. Anyway, so it's pretty straightforward. If you use MATLAB, it's pretty straightforward to plot. The result of quantization error is right here. 3-bit quantization. Okay, 3-bit quantization, and the error looks like this. The error looks like this thing right here, okay? And by the way, you can check that this is the quantization step size we're talking about, okay? This is the quantization step, okay? When we round up to integer multiple of delta, the quantization error in principle should be between, so in principle, we say En belong to the interval of minus delta divided by 2 to delta divided by 2. That's a quantization error range. But that's not what we are looking at right here. We see a few places we have exceptions, right? Did you already see the exceptions right here? We have exception where in here, here, and here. The quantization error is so negative, it goes beyond minus delta divided by 2. 比 delta divided by 2还要更多啊。The quantization error here in here, I hope you notice. Do we all notice that here? The quantization error actually is beyond the range of plus or minus delta divided by 2. What's going on? What's going on here? What's going on here? If we go back and see here, because the signal basically overflow, we are clipping the signal at the full scale, okay? Let's say the full scale is 50 millivolt. If somehow our system receives a large amplitude, then it's possible, it's quite likely. It's quite likely that our signal is too large for our representation to handle. So in this case, the error goes beyond the range because of overflow. Maybe it's not, overflow is not a good term. I say clipping, because we are clipping. Clip, 夹住, clip. We're clipping the signal between plus and minus full scale. So this is a result of clipping. But without clipping, otherwise, elsewhere in time, around in this time, we are handling the signal all right, because the signal values did not, do not surpass the full scale. The signal values do not go beyond the full scale right here. So we are fine here. We are fine here. So in here, all the quantization error is nicely in between this range. Okay. All right. So that's something to notice. Yeah. In reality, keep in mind that quantization errors can go beyond its normal range if we have clipping. Okay. The normal range being minus delta divided by 2 to plus delta divided by 2. Okay, and delta is our step size. Right? So it should be pretty clear. So that's quantization with 8 bits. Right? But how about if we, so this is another example of quantization now. At the bottom right here for plot D, we have an example of quantizing the same signal but with 8 bits. Okay, with 8 bits. So you see that the problem of clipping is less obvious. Now it's not so obvious. Yeah. The problem with clipping now is not so obvious. So I'll leave it to you. So this really makes a lot of sense. Okay, so that's where the clipping occurs. The clipping occurs right there. Okay. So that's this is certainly this plot shows us how to look at our error signal just in the time domain. In the time domain, we can look at the error signal, and it is distributed mostly within the normal range. Sometimes when clipping occurs, the quantization error could be larger than the normal range, but otherwise things are nicely distributed in between the normal range. Okay, so in the next plot, we are going to see the actual distribution. This is also part of your homework, your next homework. So if you have looked at the next homework, question number 3 asks you to make a few plots to really check the distribution of quantization error with MATLAB. Okay, so just here, but today let's look at this example from the textbook. Okay, these are examples from the textbook. So here again, we have the situation of 8-bit or 16-bit quantization. So what do you notice? What's the difference? What's the difference? What's the difference? And here we have the histogram, 长条图了, histogram, 长条图, histogram. These are called histogram, and in Chinese, this is 长条图. And so you can, just let the signal run and you collect all the values in the error signal, collect all the value, and then you just calculate the statistics. Plotting their distribution. Okay. So here, what's the difference? I ask you. If I ask you, what's the difference between the top plot and the bottom plot? Just by inspection, 用看的, by looking at it. Everybody please look at these two plots. Obviously they are different, right? So which one looks more uniform? The top one or the bottom one? Which one looks more uniform? The top one, right? The top one. So there's a kind of a practical lesson here. So the error in practice indeed looks pretty uniform when we increase the number of bits. Okay, so you jump from 8 bits, sometimes it's not enough. Sometimes not enough for the error to look uniform. Okay, but with 16 bits, then the error distribution now is more uniform. And also, please don't forget about the range, you see. Now, with more number of bits, the range of quantization error becomes narrower. So in this case, in one case, when we have 16 bits, note that the range is in the order of 10 to the 5th power. Ding, 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 10 to the 5th power, in that order. Whereas using 8-bit, naturally you have a coarser quantization step. Coarser, 就是比较宽的 coarser, coarser quantization step. This is finer quantization step, right? So as a result, the distribution is also is in a smaller range. Okay? Naturally, it makes a lot of sense. With 8 more bits, you can encode our signal more accurately with more bits. The more the merrier, right? The more the merrier. Okay, so that's this plot. So that's a check on the distribution of our error. Okay, they can look pretty uniform. Okay, when we have sufficiently many bits for data encoding, right? So was that good? Can we agree that this is our observation? Right. So if it looks uniform, we can even calculate the noise power. So that's the next cool thing I want to show to you. So now, if you're convinced that quantization error sometimes can be well approximated by a random variable, which has a uniform distribution within its range. Okay, so the range, as I mentioned, the range is from minus to plus delta divided by 2, half of quantization step size. So now we can ask this question: what's the power? Meaning, we're really saying, what's the expected value of quantization error? We can calculate the expected value of the square of quantization error. And we need to make one assumption, though. Assume that the mean, assume that our error is 0 mean. The error could be positive, could be negative, it's pretty random. So we assume that if we assume that the mean of approximation error is 0, then when we say power, that means we calculate the expected value of E square. E square is called the way we define power. Okay, so here we have a uniformly distributed random variable, and the range is random distribution is between plus and minus something, right? Have you learned how to calculate what's the expected value for E square, right? So we're talking about probability. In this course, we won't talk about probability so much, but this is the kind of one of the only opportunity we indeed we need to resort to probability. 要用到几率 So to calculate, so the power E of E square n really is we need to calculate an integral. Okay, we need to calculate an integral from within the range. Okay, within the range, and E square n times what? Times its probability density function, right? That's the way expected value can be calculated. So the probability density function is denoted as this, P. Let me just be lazy and say P, the density, the distribution is, this is a bit clumsy. Our notation is not the best, but let me just to be consistent about my notation. You know that we are multiplying our value with the probability density function and then take an integral. That's the way you calculate the expected value of any random variable, right? Okay, so please refer to your probability notes. Yeah, if this doesn't look too familiar. Yeah. So it turns out that if I remember correctly, so this is square, so we have like y. So this is what we have. And there's also a normalization factor somewhere. Okay? Yeah. So this part, 1 over delta is this part. Yeah. The density function is a constant, right? So that's that. Did everyone see that? And then we have the square. Okay, let me use another color. Then we have also the square over there. The square over there for integration. So that's why we have the third power right here. Okay? Make sense? Yeah. I'm going a bit fast, but it's pretty straightforward. Okay? This is the way you calculate the noise power. Okay? So you expect that at every sample, in average, will collect some kind of energy of noise. And the energy is right there because of our quantization error. Okay, so that's the picture. So the noise power here is, so if we just complete the calculation, the noise power now equals to, I memorized the result. The result is delta squared divided by 12. That's our noise power. Yeah. Per sample, okay, per sample. At every sample of time, we collect this much of noise. Delta squared divided is proportional to delta. Okay, delta square. So we come back to this. Okay, so this is kind of a cool little thing to know about. The noise power is proportional to the quantization step size. The larger it is, the higher noise power you will encounter. Yeah. So that's a kind of a nice follow-up for once we observe. So let's summarize right here. We have observed that the noise, when we have enough, sufficiently many bits for encoding, the noise distribution looks pretty uniform. And based on that, we can estimate the noise power, and the answer is delta squared divided by 12. Okay, so that's one nice result. And then, so please keep in mind that this plot assumes that quantization error is uniformly distributed, and which may not be always true. We have already seen an example. Using 8-bit, the distribution does not completely look uniform, right? 16-bit is fine. So in this homework, I have created some MATLAB code for you to play with. So in the code, you will load up a piece of music, the same piece of music that you had for homework number 1. Yeah, music, and then we just did some linear combination, and then I asked you to examine the noise distribution by setting different number of bits for encoding. Okay, so you can vary the number of bits, let's say 8 bits, 16 bits, 10 bits, 3 bits, you name it, okay? Yeah, and take a look at the distribution to see if they really look uniform. Okay, so, yeah. So that's one, so this assumption, keep in mind, in practice, it may not always be true, be valid, okay? So we can really put a question mark right here. It's not always true, but it's a nice simplification. It's a nice simplification which sometimes hold in practice. And there are further, we have also often we make some further assumptions. For example, number 1, we assume that the error is stationary. Okay, the error is stationary. Secondly, we often assume error is uncorrelated with signal. Uncorrelated. Yeah. So if you think about it, when we round any number to the nearest integer, the error, is it uncorrelated with our number? I mean, they can all go positive or negative, right? So this assumption that they are uncorrelated can also be examined in your homework, okay? Okay, so in the homework we have a second plot. Okay, you take a look. Okay, so then you come down to the question: what do we mean uncorrelated? What do we mean two random variables are uncorrelated? Then we need to calculate the covariance matrix and so on. Right? Okay, so keep in mind that this is, well, I just introduced to you that this is often another assumption that we make. Okay, we often make this assumption, and you can examine, you can question whether the assumption is for sure. Yeah, it is a good approximation. I do have a remark. Okay, so uncorrelated does not always imply independence. Okay, so let me just put a hashtag. Correlation coefficients being 0 does not imply independence. This is, if for those of you that have taken probability, you know that. Even if the error is uncorrelated with the signal, the original signal, that does not imply independence of the quantization error to our signal. Okay? There's independence implies, does it? Yeah. Independence implies uncorrelated, but the other way, converse is not true. So I want to mention this. And third item is how we are going to examine together next. Okay, error. We also often also assume that the error is white. You know, E of n, the signal right here, this sequence, does it look white? Does it look like it could be a white, an instance, 一个范例啊? Does it look like an instance of white noise? If I don't show you, you know, what the original signal is, okay? If I don't show you this, okay, by only looking at the error signal, would you conclude that, hey, this signal looks white? Why or why not? Okay? Does it look white? White noise. Okay. So we need to talk about what we mean for a random process to be white. Okay. So white, maybe with a bit of white means that the power spectrum of our noise is flat. Okay. White, really, the color white means all the colors are in it. We'll talk about optics or optical perception, 光学的感知啊. The color white means broad spectrum. Means if you mix all the colors, all the rainbow colors, then we get white light, right? So white means that every color is in the light, every frequency is in their signal. Okay, so in here, to judge whether or not our signal looks like white noise, we can calculate its power spectrum. Yeah. The power spectrum is really power spectrum here equals to, we're not going to review this or have a discussion in detail, but let me just tell you, this is the Fourier transform of the autocorrelation function. Roughly speaking, okay, yeah, So I'm just trying to tell you the fact that the power spectrum is the Fourier transform of autocorrelation function. That's all I want to tell you, okay? Let me write it down. Power spectrum equals to the autocorrelation function, the Fourier transform of autocorrelation function. And when all the frequencies are equal, then we say this is white noise. Okay? Flat spectrum means white noise. This is the way we can attempt to answer our question. When we're given a piece of signal, does it look like white noise? My recommendation is to check the Fourier transform of its autocorrelation function. Okay? If we check the Fourier transform of its autocorrelation function, then here is the result. Here is the result. And if I remember correctly, this is the result of using 3, 7, 11, or 15. Actually, plus 1, yeah. So in the node, so 3 plus 1. Yeah, anyway. When we use more and more number of bits, you see that, at least for this example, we see that with sufficiently many bits, then the spectrum indeed starts to look flat, okay? And that's a characteristic of exactly the characteristic for white noise, okay? For white noise. So in the frequency domain, this is the way we can take a look, okay? We can take a look. All right, any comment here? Let's take a break. Okay, let's take a break of 10 minutes, and we'll come back. We'll come back to talk about D2A, right? Yeah.你有推导出来吗？
算是有，但是我觉得有一点点小问题，因为就是我那时候我是写到他们找我，他们先问好，因为他长条图的那个纵轴是什么？
哦，纵轴啊，纵轴这好问题，我忘了讲。这纵轴就是有出现多少次？多少次？就是说，因为长条图这个东西它都有一些值嘛，值是连续值，所以一定只能够把它分成一些段落，然后看有多少次刚好落在那个区间，分成区间，然后所以每个区间产生出来有这么多次数。
所以 bit 越多，它就会
这个区间就会有越多不同的 level， 哎，而且看起来也会越平均，看起来是这样啊 ，right 啊。So did you send yours, Skylar? Yeah.
I'm like wondering, because like example 4.3 of O and S, right?
Yeah.
I'm at 4 right now. So 4.3, 4.2 is here, but
Yeah, that's strange.
it goes to 5.
Wait. Look, can I take a look again?
Yeah, sure.
This is impulse through invariance. Example 4. Wait.
Okay, because let me go to the content page. So over here it's 163, right? So I go down to, this is edition 3 as well. So it's
Okay, yeah, sure, yeah.
So 163. So from here, then I scroll to 4. So 2, 3.
Maybe I'm talking about this 3, yeah. That's why I mean 4.3.
Oh, okay.
Yeah. This is chapter 4, and this is the section number. Yeah.
Okay.
Perhaps. Yeah.
Maybe
Yeah, I didn't. Yeah, sorry, I didn't check the details, how the sections are numbered. Yeah, sure. Yeah.
我想问一个问题，就老师对法内容的 diffraction 有了解吗？
什么东西？
就是光学有一个就是进场绕射。
我很久以前学过，大概不太记得了。跟我们的课程有什么关系吗？
因为它是傅立叶光学
对
的某一个
好，
因为它是在那个什么频率跟空间频率之间做 convolution。我好奇的是，不是，应该说它在就是空间频率，它在频率里面做 convolution，然后我转到空间频率， 它做 Fourier 旋风会变成，对，然后它再转回来的话，它会变成就是说，就我想要取得它的相位，就是我想。就是这个东西，这个是我 Fourier 旋风过后的，就是这东西，就是E是那个光的强度，然后 H 是那个 impulse response，然后为什么我转回就我想取得相位的时候，会是要用取得空间频率的方式，然后给它变，
所以说我太久没有接触这个，对，这是什么课啊？
我没有，我专题。
哦，你是什么李梦林老师吗？不是。
不是，要赵老师。
OK，好，啊，对，
它这个只是一个示意而已，还是它是？
好像是真的，因为课本上他会给这个范例的话，他应该不是乱画。
可是它看起来有很不像，因为如果你说这里，
对，
理论上他们应该是要
正的，是不是？
都是就是至少也是要同一个方向，可是这里看起来没有。
但是像我这边的话是把它列成是，我们只看这个图，因为我的定义，我刚刚给的定义我蛮小心，是他减他，所以这是负的。
这是负的 ，OK，那这边呢？
这边的话可能就比较 tricky，就是说，因为你要想象有8个 bit 的时候，它是非常细，就是会有256个 level 嘛。
这是只有3 bit。
对，这是3 bit，好。他很讨厌课本上把16，反正总之16就是有多少个 number， 多少个 bits， 但课本把它定义成叫做 b 加1，我觉得超讨厌的，对 ，b 就是15啊，就是说讲来就说16个 bit 有一个是 the most significant bit， 被保留代表那个正负嘛，那剩下15个 bit，b 就是剩下多少个 bit， 所以我觉得有点烦啊，对，我刚刚特别愣了一下。对，我刚刚愣了一下，因为这还要讲这个有点烦不过课本上有写的蛮清楚的
我后来推一下，好像发现还是怪怪的。但是我遇到一个问题，我有一个问题是，就是因为因为我没有看过原题目，但我猜原题目应该是要写成，就是要证明这件事情。
对。
但是如果是要证明这件事情的话，我觉得一开始写的这个就怪怪的，因为他一开始就直接写了这个东西，这个东西是用 delta function 去推出来的。
这个东西我会把它当做它反正就是定义，有个符号了。
对，但是这个东西应该是用 delta function 推出来的，因为我记得那时候。
我们那个时候讲的时候是说就是有这个这样子一个动机啊。我们为什么这个就确实是它乘 delta 以后，如果做传统的 time 那个 continuous time Fourier transform 就会得到这个结果。但是后来重点是说定义以后，反正它的反转换是存在的，是双方可以那个可逆的，它们根本就是一个 pair， 就是 time frequency pair。对，所以我就直接把它说以后就把它想成这个总之它就是代表了原来的 signal。
所以，我想确定一下，是这个东西，它就是这个的定义吗？
我认为就直接是，我会认为在我们这门课里面就直接把这个当做是定义。
对，我是说在这门课里，但是在这个推论过程中，这个东西可以当成它的定义，因为到最后这个就是老师那个方法推出来的这个东西，也不是这个定义式，而是原本那个 continuous time signal 去连起来的。这个好像我记得老师到最后好像是一个 shifting。
那也是 Ellison 的意思，确实是那样的意思。
可是不是这样子的一个形式，所以我在想，就是这题推导过程中，这个可以当成什么？
我想想看，我的后来的推导的过程中是说，
然后那个推导过程，我后来
我知道，我的推导过程是反过来写，说 xn 可以表成什么东西的 inverse Fourier transform。然后
用那个二元性。
对，用什么？
就是那个。
用它，反正它没有用到 duality 啊。
不是 duality。
没有用到 duality， 而是用到说我就定义 xn 就是我好像是用的是
就是
xn 就是它的已经 sample 嘛，对不对？xn 是对，积分，对，
这个东西，
然后把 nt 带入进去的 t， 然后就发现说稍微化简一下 xn 可以写成某个东西的反复列反 DTFT。
就是把这个东西，好像是把积分，就是
积分范围硬是拆断的，对，硬是切断。
但是就是因为这个推出来的式子，它也是就是原本的这个东西去做一些
对，
它不是就是这个，我觉得很好奇，就是我们一开始用这个下去推导是，
我觉得可能我在想说，你当天其实我们本来想要尝试是直接这样推导，就中间卡住，应该是有办法灌得过去啊。因为我的推导方法是等于是没有走这条路，后来我决定走的是让 xn 这样子定义下去，然后自然而然呈现成它会是一个某个东西的反 inverse DTFT。那如果它是某个东西 inverse DTFT 的话，就代表它的 DTFT 就是它。我用到这样一个性质。
对，然后有一个，对，那个就是在这里的时候，老师是写，就是老师好像是把它写成什么 T2 我有一件事情很好奇是，就是这个形式的东西，就是因为我记得老师好像有把一个无限到无限的东西画成。
我是把积分分段的去积分。
然后用加强，
对，再想办法透过一些巧合，会有有些东西就会等于1。
对，再把加号放进去。
啊。
然后就是再把加号放进去，那遇到的问题是，就是因为这边前面的是，比如说前面的加号应该是长这个形式的，然后里面会有一个什么跟拍有关的东西。
对。
那就是把它提进去的时候，有一件事情我觉得有点好奇，是因为这个东西它后面不管成什么东西，它都不会是 converge 的，那为什么会最后会收敛到那个值？
好，详细的我们可能很难这样就讨论，我已经忘记细节呀，可能要重写一遍才把它讨论啊。你能够重现我写的东西吗？如果
只是说我可以试一下，因为我应该还记得。
对，关键步骤就是差不多是其实是凑答案的，这个过程是凑答案。
对，但是我后来回去想一下，我就发现，其实不知道为什么这边负无限到无限，我记得后面有一个 exponential 的形式，但 exponential 从负无限加到无限也不会是。
但是没有，我觉得好像我是不觉得有问题的啊。你推导看看，对，你推导看看，对，也许我没有想到的地方啊。Okay, so can we continue? Shall we continue? Yeah. 不要玩手机。Yeah. Can we continue? Okay, so we are right here. We were right here. Okay, 10 minutes ago. So I'm just quickly telling you a fact that the Fourier transform of autocorrelation function is the power spectrum. So if we just take, so this page really says a result. Okay, shows us some results. Result of measuring our quantization error signal and then shift it and multiply and then take the expected value. That's the autocorrelation function right here. Okay? Autocorrelation literally, 字面上, autocorrelation literally means to correlate with oneself, right? With the signal itself. What do we mean exactly? Shift the signal and correlate it with itself. Calculate the expected value in that. And here, of course, again, we assume that based on the assumption, which is often pretty true, that our signal is zero min, okay, before considering its autocorrelation function, okay. So the Fourier transform was something being flat, okay, being flat. But if we ask the opposite question, the inverse question, which function corresponds to has a flat spectrum? What function has a flat spectrum? The delta impulse function, okay? So if this is flat, then that implies, so some observation can be made, okay? We can make an observation that if the spectrum which often denoted as the what? X e to j omega, okay? Yeah, this e stands for error. That e is exponential, okay? Not a good notation, but you know, if the spectrum is something's spectrum is constant, then that means the autocorrelation function is a delta function, okay? Then that means back in the time domain is a delta function in the time domain. And this is important. Okay, we want to introduce this. Yeah. That means that in the time domain, autocorrelation function is the delta function, basically maybe scaled by a factor. Okay, so that means, in other words, this we have the expected value of E times E shifted is a delta function. It's basically delta m, maybe times a kind of the error, its power. Okay, times its power, times the noise power, which is what? Where sigma squared equals to what we just said, delta squared divided by 12. Yeah, put a question, exclamation mark here. Yeah. So if the spectrum really is wide, then we know the autocorrelation function is a delta function scaled by the power, and the power is delta squared divided by 12, as we previously derived. So everything connects together right here. So another comment now in the time domain, what does it mean for a noise to be white? It means that samples, in between samples, the correlation is 0. Like any sample is uncorrelated with any other sample. That's the meaning of having a autocorrelation function which is delta function. Is that too fast? If you shift the signal a bit and then calculate the expected value of the product, and if that number, the answer is 0, that means that the signal itself is uncorrelated when you shift it. When you shift the signal, even just by one sample, is entirely uncorrelated. Every sample is uncorrelated to the next sample. Okay? So white noise needs to be independent, identically distributed. Okay? Yeah, I mean, so oftentimes this is a result of assuming that the error signal, in this case, assuming that the signal is independent, identically distributed, then we have white noise. Yeah. Identically distributed so that the power is constant, the noise is stationary. Identically independent implies uncorrelated. So the signal, the error signal itself is, we observe that it is uncorrelated to itself, shifted even by just one sample. Okay? Every sample is uncorrelated to the next sample. That is what is implied by a flat spectrum. A flat power spectrum implies that every sample is uncorrelated to the next sample. That's what it means for noise to be white. Okay? Yeah. So so this is really a lot of kind of observations can be made. We can make a lot of observations right here, just really even by looking at this one figure. Okay, flat spectrum, uncorrelated in the time domain. When we talk about autocorrelation, and also the noise term seems to be scaled by delta divided by 12. Okay, delta divided by 12. So you can see that, for example, if I ask you, so here is another kind of nice exercise. If I ask you, what is the difference here? When we increase the number of bits from 11 to 15, okay, how much can we lower the quantization noise power in dB? In dB. When you have 4 more bits, how much can we lower the quantization error power, right? That's something that we can talk about. And if you see, so usually the answer, there's an answer of 6 dB per bit. We gain 6 dB of signal to noise ratio when we increase, we are given 1 extra bit, okay? So here, as you may notice that the difference here seems to be about 24 dB, and that agrees with this prediction. When you have 4 more bits, when we have 4 more bits, 15 versus 11. When we have 4 more bits, note that here indeed, we increase our signal-to-noise ratio by 24. Okay? Because for every extra bit we increase the performance by 6 dB. Okay? And that agrees with the fact that power is proportional to quantization step square. Okay, so any comment? Before we move on. Well, anyway, so please, now you can work on homework number 2. Okay, homework number 2 is there's some experiment, a MATLAB experiment for you to run. Okay, so we'll be able to look at the noise distribution and to look at to examine if the quantization noise is uncorrelated with the signal and so on. Okay, and we can calculate the noise power. We can calculate the noise power and listen to it. Okay, this is music, right? Seriously, in this homework, you will listen to the quantization error and tell me, I need you to tell me, does this sound like white noise? Does it sound like white noise? This is your exercise, okay? In this homework, you will really listen to judge whether the quantization error signal sounds white when you listen to it, okay? Okay, so next, let's just briefly talk about, review the entire chain. I think this is a good time. So the entire chain for processing our signal is shown in here. That's the entire chain with continuous time signal to the very left. And then we let it go through an anti-aliasing filter, a low-pass filter, so to speak, so that we can expect that after sample and hold, there's no aliasing. Okay? No aliasing when we sample at least 2 times the bandwidth. Okay? Then there will be no aliasing. And then from there, we have sample and hold so that hopefully we have enough time to encode our number in binary as binary zeros and ones. And we already know that there will be some quantization error, which can sound like noise, sound like white noise. And then let me just give you a kind of a promise. Okay, so in the rest of this semester, we pretty much focus on this part. Okay, we focus on what we call discrete time processing of continuous time signals. Okay, we process our continuous time signals in discrete domain, in the discrete time domain. And for the rest of this semester, we pretty much just stay right here, stay within right here. We focus right here. But then we want to know that after we process, or after we spend the entire semester talking about digital processing, then still, this is a good time to briefly mention how we should appropriately convert our output back to the time domain, back to the analog domain and continuous time. Okay? So namely, you find two steps. One step is called D to A converter. The other is called compensated reconstruction filter. Okay, yeah, two steps. And these two steps should be equivalent to what? To sync interpolation. Remember that we said after our digital spectrum should look like periodics for every 2 pi, right? For in the omega domain, zero frequency. And then we mentioned that we ideally apply a low pass filter, which corresponds to sync interpolation. Which corresponds to sync interpolation, which may look like convolution with a kernel function that looks like a sync function. Okay, so this is in the time domain. Convolution time domain, multiplication in the frequency domain. So I want to mention before we move on, please, I want to just tell you that you'll see later that these two steps should correspond to ideal low-pass filtering. Okay, ideal low-pass filtering can be decomposed into two steps. Step 1, step 2. Step 1 being DA conversion. Step 2 being we need to apply a compensation sort of filter. Okay, and what is that? So first step, the D to A conversion is pretty similar to sample and hold. It's actually, it's called zeroth order hold. It's called zeroth order hold right here. Okay, and it's best explained by this figure. When we say zeroth order hold, we mean, for example, if our quantized sample, okay, if our quantized sample is marked by open circles, 空心的圆, open circle, If our quantized sample is marked by this, then each time we see a sample, we just hold it for time t to go back to the continuous time domain. Is that clear? You receive a number, the output of your computer, of your GPU, of your CPU, of your MCU, and so on. You see the number, then you hold it for t. Receive a number, and then hold it for t. Receive a number, and hold it for t. Receive a number, hold it for a length of t. And this is called zero order hold. Zero order means flat, okay? No slope, 没有斜率. Zero order, just hold the value for t. It's pretty simple, okay? So now, by doing this, we are already going back to the time domain. The resulting signal should look like this. Let's try. The resulting signal in continuous time should look like this. Hold, and hold, and hold, and hold, and hold. And it can only have finitely many possible levels because it's represented only by a few bits. Okay? So this is the result we get, kind of a piecewise constant signal. After zeroth order hold, it's already back in the continuous time domain. Now, but the original signal should look like this. It should be smooth, right? So how do we kind of smooth our step-like function so that it becomes smooth? We need some kind of smoothing, okay? Some kind of smoothing. So here is the deal. The recommendation is to use a filter like this. If we can construct an analog circuit which has this low pass effect, okay? This is an analog filter. The desired analog filter we say after zeroth order hold, the frequency response, its frequency response should look like concave up between plus and minus Nyquist rate. Yeah. Remember that t, pi divided by t, this is Nyquist rate. Nyquist frequency. The answer that we want to design, okay, we desire to design a filter whose frequency response is concave up like that. Why? There's a reason. The reason is because zeroth order hold introduced this gain profile. Okay? Zeroth order hold. So if you just calculate the Fourier transform of zeroth order hold, this is the impulse response of zero order hold. Okay? HT is the impulse response. Of zero order hold. That is when we receive an impulse, it holds on to the value for a time t, okay, for a time big T. Okay? So in the time domain, the impulse response, if you plot the impulse response, is 1 between 0 to sampling period and 0 elsewhere. That's the impulse response for our zero order hold. Then, if you accept that, if you understand that, yeah, if you see that, then the plot on the right shows us the real result after Fourier transform, the frequency response of this system. So this is nothing but taking the Fourier transform, and now we reach what we have is the impulse response of zero order hold. Okay? So that's a frequency response of zero order hold, which is not an ideal low-pass filter. Remember that we desire the combined effect to be ideal low-pass. Okay? So how do we change this frequency response to become ideal low-pass? So simply because here we have concave down, here we need concave up. So that when we multiply the reconstruction response with the Fourier transform of zero order hold, the result becomes a constant. That's a kind of the thinking behind the design. Okay, that clear? So we want yeah, I hope. So if we create a name, okay. So if this is h of I forgot what's the notation. Let me take a peek. Yeah, h0. Yeah. If h0, if this is the Fourier transform of that, right? Yeah, that's clear. Small h in time, big H in frequency. Okay. So if the frequency response, the Fourier transform for zero order hold is denoted as this, then we want a reconstruction filter such that we want the reconstruction filter will multiply with the concave down. We want the result to be 1 in the pass band, and 0 elsewhere. Okay? So that's why the desired analog filter that we apply after zero order hold should be a concave and also bandpass. Okay? Concave bandpass filter, which looks like what is shown right here. Concave up, bandpass, so that you can agree that when we multiply the zero order hold response with this reconstruction filter, hopefully we have nearly ideal low-pass filtering. Hopefully the combined effect will be ideal low-pass filter. Yeah. In your dream. Okay. Yeah. In your dream. Yeah. If you're interested, please talk to any other professor who specializes in analog filter design, analog circuit design. Okay, but you know that's a goal. Okay, that's a goal, right? So that's as much as I want to talk about D to A conversion. Yeah, reconstruction filter being concave off, and there's a reason. Okay, there's a reason to compensate for any change of gain due to zero order hold. Yeah. So this this expression summarizes in everything that's happening. Okay, it summarizes everything that's happening. First, we have anti-aliasing filter. First, AA stands for anti-aliasing. And then we process our signal in the discrete time domain. And then zero order hold. And then we have a reconstruction compensation filter. Yeah, we have a compensation filter for reconstruction. So just tell you the good news is that in the rest of this semester we'll simply focus on this middle part. Okay, we focus on operations that happen in the discrete time domain. Okay. Yeah. So that concludes all the material I want to share with you for chapter 4. Okay. So for this lecture, if you are interested in further discussions, all details, please go refer to textbook. There's section 4.8. Okay, I think it's section 4.8. There's a section. So, yeah. So I asked my TA to. So some of you actually, one of you reported to me that you may appreciate if we tell you what our materials are. Where do we find the materials in the textbook? Okay. So I will ask my TA to announce where we can find the lecture materials in the textbook. So after every lecture, please expect that TA will tell you, TA will announce where to find these materials in our textbook. Okay, so please don't worry. I think for the student who suggested to me, okay, that we should do that, and we will do it. We will announce where to find the materials. Okay. All right. So that's let's take a kind of 2 minutes break to reflect what we learned, and then we'll switch to my next lecture. 休息个2分钟吧，休息2分钟。我知道有老师会那个 ，Let me say in Chinese some announcement. I'll translate that to English later. Okay. 我知道有老师那个会有 QR code， 是不是？有些 professor 会有 1 minute reflection. Have you encountered any professor who shows you a QR code so that you can ask question by scanning the code? Slido. 有是不是 Okay. Actually, I think we have time. Yeah. Do TAs know what they are talking about? Using a Slido link, and we leave some empty time like this, so you can ask question while you still have it. Okay. Yeah. Do you want to do that? Do you want to try that? Yes? Yeah. Does anyone want to try that? Maybe we can try that. Okay. Yeah. Or 我知道对呀，应该可以的，应该有机会啊。Okay. All right, so I encourage you to, while using this time of reflection to, kind of, if you can come up with any question, this will be a good time. But otherwise, I may continue into our next lecture. Okay? Continue into our next lecture. So let's now move on to linear and time invariant systems. Okay? Linear and time invariant systems, and the title of this lecture is Introduction to LTI, linear time invariant systems, and the transform. And actually, I did my homework. Okay, so in the textbook, I checked that the corresponding sections are right here. It's actually we are covering in this lecture. We are going to cover some or review some content in chapter 2 and chapter 3. Okay, these are the corresponding section numbers in the textbook. Okay, so let's start. Let's start slowly. So in our discussion to linear and time invariant systems, the first thing is to define our terminology. When we say linear time invariant, that really means linear and time invariant, two properties. These are two different properties. A system can be linear or time invariant or both. So when a system is linear and time invariant, then we call the system LTI, linear time invariant. Okay? Really, it means linear and time invariant. Both properties have to hold. Okay? So we need to talk about the key idea is impulse response. Okay? So what do we mean impulse response? In the rest of this semester, mostly we are going to denote our input by X and output by Y. Okay, X being the input, Y being the output. And then we have seen this many times. There is this delta function whose definition is equals to 1 at time 0 and 0 elsewhere. That's the delta function. So imagine that we put, now the input is delta function itself. Imagine that we have a system. The input is the delta function. And the output h of n is called the impulse response. Okay, that's the definition. The impulse response of this system, of the system. So for the name's sake, impulse response means a system's response to delta function because delta is an impulse. Okay, in discrete time. Okay, so that is just nothing but a definition. But then the important property here, the kind of take-home message, okay? This, the take-home message for this lecture really is that about complete characterization. Let me repeat that, complete characterization. 完全的刻画, complete characterization, what does that mean? We say that an LTI system is completely characterized by its impulse response defined in this way. Okay? It's completely characterized by its response to the delta function. That is to say, in what sense? In that, given now, if we know h of n, if we know the response to delta, if we know the system's response to delta function, which is denoted by h, we know h, then for any arbitrary input, we can calculate the output, and that's what we mean complete characterization. That means we know how to predict the output for any arbitrary input. The system's behavior is completely understood. That's why we say this system will be completely characterized, 刻画 被刻画啊 by h of n. In that, we know exactly how to calculate the output. And the output turns out with a convolution of our input with the impulse response. Okay? In that sense, we completely characterize the system. So to repeat, again to review what convolution means, here when we convolve, the notation goes right on the right. Okay? When you have one signal and another signal, we convolve it, and the result is a third signal. That's the notation, okay? Now please contemplate on this notation, okay? Here I'm emphasizing that the result itself is a function of n. Okay? The notation here, that's our symbol for convolution. So convolution is defined as this. In one or the other equivalent way of writing down the summation. So you can write down the summation as there is an index k, which goes from minus infinity to infinity. And then we are taking a look at the k sample and then flip h with in time, reverse h in time, and then perform the inner product. Okay? That's a definition of convolution. And it's trivial to see that this is just by changing introducing a change of variable, you can also write here h of k times x of n minus k. The results are the same. The results are the same because k is simply a dummy variable. You can change the variable. Yeah. So doesn't matter. Okay. Doesn't matter if you write it this way or this way, the results are equal. Okay? Convolution is well defined. Okay? And we know this is a take-home message, and I think we do have time to show why this is true. Okay? For any system that is linear and time invariant in the discrete time domain, then we know how to calculate its output, the output it produces for any arbitrary input, because the calculation simply goes this way. We convolve our input with the impulse response, then that's output. That's output any linear and time invariant system should produce when it receives x of n as its input. Okay? So that's a take-home message. But now it comes down to the question. We need to fully define, to exactly, accurately define what do we mean a system being linear and what do we mean a system being time invariant. Yeah. Okay, so we need to first write down a mathematical definition for linearity and the time invariance. Okay, and let's do that. So linearity means if xn is input and the signal goes through a certain kind of system that roughly speaking we denote at h, script h, 草写的 h. Okay? If you use a script h, 草写的 h, to denote, to kind of represent a system. And again, if the output is called y, then linearity means that h, if h of one signal, if for this input the system produces this output, and if for another input the system produces a corresponding output, so if x1 produces y1 and x2 produces y2, okay, then linearity means what? Means when we linearly combine the input, the output also linearly combines in the same way with the same coefficients. Can I say that again? Yeah, I think you guys have all learned linearity. Linearity means when we linearly combine the input, now this is a linear combination where alpha 1 and alpha 2 are constant, okay? And then send it to our system. The result will be the same output and combined with alpha alpha 1 and alpha 2. The result will be alpha 1 times the corresponding output plus alpha 2 or corresponding output for any x1, any signal x1, x2 n, and any alpha 1 up to constant. Okay? That's what we mean. When this property is satisfied, we say the system is linear. When this property is satisfied, we say the system is linear. It's about the relation between input and output. Okay, yeah. So far, so good. So that's how we define linearity in the discrete time domain. Very easy. Now, how about time invariance? Time invariance means that when the property of the system does not change over time. So anytime it receives a signal, maybe now or later, but the response should be the same. Doesn't matter if we use the system today or tomorrow. If we expect the same outcome, then the system is called time invariant. Invariant against time. 对于时间是不变的啊。Invariant against time. So then how do we write it down? How do we write down this mathematical property in our notations? So with our notation still with this same convention, still input being x, output being y. Okay. Yeah. And so time invariance means that if we delay our signal by m samples, where n is the time index, the dummy index, m, the second one, this is a delay, okay, or advance, depending on the sign of m, okay, a fixed delay. So if we send our signal later, m samples later to our system, we expect the output to be also delayed by m samples. So if for any input and any fixed samples of delay, if the output will also be delayed by m samples, then we call the system is time invariant because its behavior is the same. When we delay the input by m sample, the output is also delayed by m sample. There's nothing trickier than that. Okay? The output will not delay by 2 times m samples. Okay? So nothing that tricky. Okay? It's pretty straightforward. So if this relation is true for any given input and for any given fixed amount of delay, we have the property that the output is also the same output but delayed by m samples. Yeah. Then we say the system is time invariant. Okay. Yeah. So linearity and time invariant, as you may see now, are 2 different properties. Okay. So next, I like to prove that indeed, when a system is both linear and time invariant, when a system is both linear and time invariant, how do we show that the output will be the input convolved with the impulse response? That's the next thing we want to check. Okay, assuming that the system is LTI, linear and time invariant. Okay. So the goal here now to show that now for an LTI system, y of n equals to, that's our purpose, okay, x convolved with h in the time domain. That's our purpose. Then first, this is kind of a nice trick. Okay. First, I recommend writing our signal. I recommend this expression. Okay, let's take a look. Right. I recommend this expression, and it will become useful. Okay, but let's take a look at this expression together. For any signal x, I claim to you that x can be written as a summation of delta impulses. That x, any x can be written as a summation of delta impulses, each scaled by the height of x at that time. So here we have delta shifted to the right by k sample and scaled by the height of x of k. And when we sum up or collect all the terms, then we get back the signal. That's a pretty straightforward idea, and I want everybody to see it. Okay, why? And yeah, some of you might have seen this. That the reason is because, let's take a look. If we have x0 times delta n, that's one signal. And if we have now next, we have another signal. It's still a delta function, but shifted to the right by one sample, and the height becomes x1 delta n minus 1. Let me draw a third plot, and you'll see what we're getting at. Okay? And the third sample, let's say, is here. Delayed by one sample, then its value is the height is x2, but now its location is at time n equals to 2, where n denotes the time axis, 时间轴. And so on and so forth. When we sum up, what do we get back? We get back all the samples, and the heights are all right, the places are all right. Yeah, the sum becomes one sample, this height, next sample, that height, sure. The next sample, that height, and so on, and so on, and so on. So we get back the original signal, okay? So I'm trying to convince to you that indeed for any signal, we can write it down. We can express our signal for any arbitrary signal as a sum of delta impulses. Or you can see that we can express any signal as the convolution of the signal itself with the delta function. Okay. And hopefully, I'm hoping to help visualize what's going on. Okay. For any signal, we can decompose it into the sum of all its samples, so to speak. Right? In discrete time. In discrete time. Can we agree on that? Can we agree on that? And now we have some time to talk about the consequence. Okay? Yeah, big deal. We have an expression for another way to express our signal as sum of delta. Okay? But what is a consequence? A nice consequence, 导致的结果啊. A nice consequence is this. Then, because of this, therefore, when we talk about the signal being processed by our system, sending x to h, right? System signal. When we talk about the system, now it is processing our signal, and our signal is the sum of xk delta n minus k, symbolically. 符号上是这样, right? And if the system, we know the system is linear. If the system is linear, what happens? Can we move the summation to the outside? Because of linearity, right? So because of linearity, we move the summation to the outside. And actually, xk right here does not depend on time, right? Nominally, 字面上, it does not depend on time index being n. So here, really, what we have here is we can move the system the operation inside the summation. And now we have this. Okay. And this is because of linearity. This is because of linearity. And my last equation, how about the other property, time invariance? That property has not been applied yet, right? Yeah. So now, when we look at this intermediate outcome right here, now on the right, we have the system processing this signal. And this is our delta, the response to delta signal, right? The response to delta, we know the result is H. But shifted by K samples. Because now here, because here the input is shifted, the input right here is shifted by N samples. So the output should be still this response function, but shifted by K samples. Okay? That's right here, okay? But then if we just copy everything, then we get our result. Okay, then we get our result. It's as simple as that. Okay. So by 2 steps, we checked, okay? This is, we'll stop right here. We have checked that because of linearity and time invariance, and because of the way we define what impulse response is a response to delta function. Okay? Impulse response is the response to delta function. Because of our definition and the property, the intrinsic properties of linearity and time invariance, we conclude that now we know how to predict the output given any input. The answer is we only need to calculate a convolution. We need to convolve the input with our impulse response, which you may be able to measure. Convolve H and X, then you get the output Y. Okay. Yeah. So next week when we come back, we'll officially review the transform, and there's also a corresponding convolution theorem. Convolution in the time domain implies multiplication for the Z transform. Okay. But anyway, tomorrow we will have the discussion session for homework number 2. So please take a look and remember to sign up. And thanks for being here. Okay. I hope the other students enjoy the video. Okay. Yeah. See you tomorrow. See you. Yeah.
我想询问就是，我不太懂为什么老师在讲那个D to A converter 的这个阶段有讲2个frequency response 的函数嘛？
对
这2个相乘，为什么一定要等于1啊？我不太懂原因是什么？
等于1的话，在 passband 等于1，在另外一张，因为我们在先前讲 D to C converter 的时候，有建议说大家要去设计一个 ideal low pass filter。
哦，是它是一个
对，要，那这个就是两者的效果相乘以后要应